We're gonna go through the end of worksheet 3 today. So we're gonna start with this question about a person diving from a platform. And so when I'm going to do a problem like this, it doesn't ask us to do a force diagram. It's not actually required for this one. But I like to draw pictures because I feel like with pictures, sometimes you can see things that you don't when you just read the words on the page. So I'm going to draw, here's my water, and then my platform. This is my ladder here, and I've got a platform sticks out. Has anybody jumped off of a 10-meter platform? How high is that, guys? 30 feet? That's a 3-story platform. I would not be first in line for this. Anyway, my mom was a competitive diver in high school. So she might, I don't know, she might have dove off something this high. So there's our person, and they're going to go off this platform that is 10 meters above the water. The person has a mass. So it's one of our force things, a mass of 65 kilograms. Whoa, too many letters. What's her speed as she enters the water? So we're trying to find the speed down here, right? Which is a little like a final velocity. We need to know some other stuff, right? If this is going to be a force thing, and we also need to know some stuff about motion, we're trying to find our final velocity. We don't know that yet. Some other things that we do know, though, is if this person is going to be jumping off the diving board, that they're going to have an acceleration due to gravity of minus 10 meters per second squared. So that's something we know. We also know their initial velocity because this person is going to start from rest. So we know that their initial velocity up at the top is going to be equal to 0 meters per second. We also know that the distance that they are going to travel is going to be equal to 10 meters. Now, one thing about that distance is that it's downward. And so with our acceleration, we gave a value that was negative because that was a downward acceleration. And we need to be consistent with that sign for the other values that we have here. So we're also going to make that distance minus 10 meters. So we're going to be going in the negative direction as our diver falls. So we're asked, what is her speed as she enters the water? Well, we're going to be able to figure this out with our motion information because we've got a final velocity, an acceleration, initial velocity, and a change in position. And so if we take a look at, I'm going to grab a separate page here just so I don't have to flip all the time. So if I take a look at my equations, the one that I'm going to use, since I don't have time, I'm going to go all the way down to this third one here. My final velocity squared equals initial velocity squared plus 2 times acceleration times my displacement. So that's going to be my equation. And what we're going to solve for is our final velocity. So our final velocity squared is going to be equal to our initial velocity, which is 0, right? So we're not even going to need to worry about that. So we just need to know 2, whoops, this should be 2ax. 2 times our acceleration, which is minus 10 meters per second squared, times our displacement, which is minus 10 meters. So if this is equal to final velocity squared, one thing we're going to need to do is find the square root of this. If we have a negative value in there, then we have a problem. Sydney. Yes. Okay, so when I draw a little triangle, that's an abbreviation for change. So the way that it works, if you see change in x, it means the final position minus the initial position. It's, for the purposes of our class, it's not that different from just saying x.
And since they're not like they're going down and not moving, is it changing y or is it switching like
It doesn't really matter. If you want to use change in y, that's okay. The reason that I just keep using the x is because because the equations are written with x's, and what I don't want to do is make it confusing by just duplicating everything. So if I said I'm trying not to create confusion by saying that like the horizontal one has delta x and the vertical one has delta y. Yeah. So as long as you guys are okay with the idea that it doesn't, as long as you're consistent within the problem of which way you're going. So you couldn't use a horizontal, a side to side acceleration and a vertical distance. That wouldn't work. You need to make sure that when you're applying one of these equations, that you're using only vertical things or only horizontal things. And then it's okay. If you want to use change in y, if a student wrote change in y on their paper on a test or something, that wouldn't phase me at all. And that would absolutely be okay. Yeah. Is that all right with you? Okay. Yeah, so it just means the distance traveled. And so as long as you just look at it and go like, okay, that's the distance, and I have to be consistent about horizontal or vertical, then that's absolutely okay. I try to keep it so that you guys only have to work with a couple of equations, and then you know how to use those really well, instead of having like a page of equations where you have to filter through like which one you want to use. I don't know. I mean, it's kind of both ways, because we could just do three, or I could start rearranging all of these. So another really common version of this guy is to write out acceleration equals final velocity minus initial velocity divided by change in time. But they're not like it's a different way to write the relationship, but it's not a different relationship. They're really they're really just two versions of the same thing. And so I see that a lot with physics stuff that other students have or that my friends use sometimes, where they have like a humongous list um, of equations. If that's something that works for you guys, like we can come up with that. But I just having like I just I prefer to just have a few and then know which things to use and which things not to use. So with our final velocity, because this is a squared value, if this number isn't a positive, then we're at a point where to solve this, we have to do the square root of a negative number. That doesn't really work, right? It's not really a physical entity that we can deal with. It's a theoretical math thing. So if you get to the point where your answer doesn't make any sense, take a look at your signs, because that's the most common thing that students do when we're getting to these types of problems is they forget to change the signs. So here our final velocity squared is going to be equal to 2 times minus 10 times minus 10. So this is going to give us a value of 200 meters squared per second squared. And so our final velocity is going to be the square root of that. So we're going to have the square root of 200, and the units will be the square root of meters squared divided by second squared. So that ought to be meters per second for our final units. I can't do square root in my head. I admire those of you who can. So I got 14.1 meters per second. I'm going to add another thing about this too. So we can't have a negative value inside the square root, but you guys probably recognize from math class that when you get an answer to a square root, it's not just the positive version, right? It's either going to be positive or negative. And we have to decide which one is the correct solution. What do you guys think? If our person is falling in the negative direction, should we choose the negative or the positive value for their velocity? Which direction are they headed? They're headed down, right? So if they're headed downwards, we need to choose the negative value. It needs to be minus 14.1 meters per second for the final velocity for our diver. You guys have any questions about that one? And we did a lot of sidebars on that. For the second part, it says she comes to a stop 4 meters below the surface of the water. Find the force on the swimmer by the water. So we're headed towards force. What we already know is that her mass is equal to 65 kilograms. What we need to do to find the force is we also need the acceleration. And that's something we don't already know. We would know her acceleration if she was falling through the air, right? But we don't know about her acceleration here. In order to solve for that, we need to know her velocity at the top and her velocity at the bottom. And this is a little bit strange because here we have a diver that fell. We figured out what her velocity was at this point. We determined that it was minus 14.1 meters per second. And that's going to be the same as her new initial velocity, right? That's her velocity when she enters the water. So for the second part, we're going to consider that as her initial velocity. What's her final velocity going to be after she goes 4 meters, 16 feet underwater? What's her velocity if she comes to a stop? It's 0, right? So 0 meters per second is her final velocity. So now we're going to be using some things about motion to figure out what her acceleration is. So initial velocity is minus 14.1 meters per second. Final velocity is 0 meters per second. And the other thing that we know is the distance, which is going to be, again, minus, and then 4 meters. So just like, not quite just like before. We know initial velocity, final velocity, position. We don't know time. We're trying to solve for acceleration. So the thing to use is going to be our same equation that we used for part A. Final velocity squared equals initial velocity squared plus 2 times acceleration times the change in position, or x. Our final velocity is 0. 0 equals, look at this number squared. We already know that, right? Because that's how we figured out our velocity in the first place. I'm just going to write 200 meters squared per second squared right there, plus 2 times acceleration times, needs to be minus 4 meters. There we go. I'm going to subtract 200 from both sides. So minus 200 meters squared per second squared equals minus 8 meters times acceleration. So my acceleration is going to be minus 200 meters squared per second squared divided by minus 8 meters equals. Minus 200 divided by minus 8 gives me 25 meters per second squared. Should that be a positive value? Whenever we have acceleration, it's gonna give us a direction that the motion is changing. And so when our person hits the water, they start to slow down, right? So if they're slowing down, we would expect the acceleration is in the direction opposite their motion. It's not helping them to speed up through the water. They're not going faster. They're going slower. And so that acceleration is going to be the opposite direction. So if our motion of our diver is downward and they are coming to a stop, we need to have an acceleration pushing the opposite direction that's changing their speed so that they come to a stop. It turns out when they hit the water, the thing pushing back up on them is buoyant force, right? Gravity pulls you downward, but buoyant force pushes you upward. And since this person is coming to a stop, that buoyant force must be pushing upward so that they slow down and they don't fall through. Well, now that we know what our acceleration is, 25 meters per second squared, we can use that to figure out our force. So to find that, I'm going to draw a line so I can do a new calculation. We need to do mass times acceleration. Our mass is 65 kilograms times our acceleration of 25 meters per second squared. I got 1,625 newtons, which seems kind of like a lot. But how much does our person weigh? Person weighs 65 kilograms. So we know that they're pulling downward. Sorry, the Earth is pulling them downward with a force of 650 newtons. And the water is pushing up with 1,625 newtons. So it's almost twice as much as gravity. So that's why they start to slow down, because the water is pushing back with more force than gravity is pulling them downward. How you guys feel about that one? Feels okay? You guys have any questions about it? No? Okay. So we're going to go to problem number 4. Do you guys have moms that do this? Like if your car stops suddenly, they put their arm out next to them so that you don't go through the windshield? Yeah. My mom did that too. I think it's like one of those mom and reflex things that like happens all the time. The worst is when it's like a bag of food in the car though. And this has happened more often since, coronavirus, but food sloshes on the floor. My kids are young enough they don't ride in the front seat, so I haven't had like the front seat thing happen to me yet. Anyway. Okay, it says during a head-on collision, a passenger in the front seat of a car accelerates from 15.3 meters per second to rest in 0.1 seconds. So remember, acceleration can be either when you go faster or when you go slower. And here it looks like slower because we're going from a velocity that's greater than 1 to rest, where we have a velocity of 0. So the first thing it says is calculate the acceleration of the passenger. So that's what we want to know. We already know that our initial velocity is 13.3 meters per second. We know that our final velocity is 0 meters per second. We know that our change in time is going to be 0.1 seconds. So that's how long it takes for the car to come to a stop. So if we've got acceleration, 2 velocities, and time, we can look at our chart on the front. Look at this. I already rewrote it. So we can use this first equation to figure that out. So our final velocity is equal to acceleration times the change in time plus initial velocity. And we can rearrange this to solve for acceleration. So our acceleration would be final velocity minus initial velocity divided by time. So to do that, I moved initial velocity to the opposite side by subtracting it from both sides, and then divide it by the change in time to isolate acceleration. Our final velocity is 0 meters per second. Our initial velocity was 13.3 meters per second. We're going to divide that by 0.1 seconds. So if I have minus 13.1 divided by 0.1, then I end up with an acceleration of minus 131 meters per second squared. That seems pretty abrupt. Every second, the velocity was changing by 131 meters per second. The driver of the car holds out his arm to keep his 25-kilogram child who is not wearing a seatbelt. Always wear a seatbelt, guys. From smashing into the dashboard. How much force must he exert on the child? So if we know our acceleration, which is minus 131 meters per second squared, and we know the mass of the child, 25 kilograms, we can figure out force with the Newton's second law and just multiplying those two things times each other. So we've got our 25 kilograms times minus 131 meters per second squared. So the force forward of the child is going to be 3,275 newtons. And so for the person to hold them in place, they're going to need to push back with 3,275 newtons. If you were holding up enough mass that you had to exert that amount of force, how much mass would it be? Like if you're just holding up a mass. It'd be this value divided by 10, right? So it'd be 327 kilograms. How do you guys feel about holding 300? No, I don't think you can do it. I don't think I can do it. So that would require a lot of force. There's no way that this person's gonna be able to hold that kid in the seat. That's why you should wear your seatbelt. What's the weight of the child? Keep in mind that weight is a force, not a mass. And so when you calculate the weight of the child, you're going to need to figure out, let's see. We're just going to write our same usual equation, except for weight is going to be our mass times minus 10 meters per second squared. It's always going to be mass times acceleration due to gravity. So for our child here, we've got 25 kilograms times our minus 10 meters per second squared. And so this child has a weight of 250 newtons. I know that it feels weird, right? Because we want to say, we use these interchangeably, just in everyday language. But for physics class, weight's a force. So I'm asking you to tell me how many newtons of force that child is experiencing. If you see a question like this on a quiz and you tell me 25 kilograms, you told me the mass of the child. So just be careful about that one. Lastly, convert the forces in parts B and C from newtons to pounds. What are the chances the driver will be able to stop the child? All right, so in part B, we've got 3,275 newtons. We're going to use dimensional analysis to convert this. Since 1 pound is equal to 4.45 newtons, we can use this conversion factor to figure out how many pounds of force we would need. And we end up with 3,275 divided by 4.45 for 735.9 pounds. Some of you guys probably do some weightlifting downstairs and recognize how many pounds that is. This is basically 4 or 5 adults, 4 or 5 average adults, right? Lots of people. For part C, we have 250 newtons. We could do the same thing. 1 pound is 4.45 newtons. So that's 56.2 pounds. You think the driver's going to stop the kid from hitting the dashboard? Probably not. All right, what questions do you guys have? Any questions? No questions.